we now introduce spectral sequence. So the idea of spectral sequence is to keep on taking homology of a chain complex till it stabilizes. So we have to understand this. So whenever a spectral sequence is given to you, you need to picture a sequence of pages. So say that you have a book in your hand and it has pages in it, and there is a chessboard on every page. Now on every square of this chessboard there sits a module. So every square is associated to a module, and in this module there is an arrow going in and an arrow coming out. So on the rth page the arrow is such that you move r left and r minus 1 up. So on the rth page you move r left and r minus 1 up. So this is for homology spectral sequence. So this is for homology spectral sequence. So let us see this in pages. So let us see page number 1. So this is how page number 1 will look like. On the page there is a chessboard. In every square there is a module sitting. So we are on the first page. So r left, you move 1 left and 1 minus 1, so 0 up. So 1 left and 0 up. So you have a module here, you move here 1 left. So there is an arrow coming in, also 1 left. So associated with this module there is an arrow going out, but the arrow also comes into it from the previous square. Similarly here the arrow comes into this module from the previous square. So you can see it like this. So this is the 0 0 position we have seen. So entire coordinate plane is sitting like this, and you have module. So arrow is going into every module, arrow is coming out of every module. So this we have drawn specifically, but you can just pick up any square and you know in this square the arrow is going out like this and coming in like this. So this is page 1. So let us now see page 2. So on the second page you will move 2 left and 2 minus 1 up. So 2 left and 1 up. So say you are in this square, so you have to have an arrow going out of the square and arrow coming into the square. So arrow going out of the square comes from, you have to see 2 left, 1 and 2 and 1 up. So here again, so arrow coming into the square has to come from here, this module here, which goes 2 left and 1 up. So arrow coming into this module comes from here, which is 2 left, 1 up. So you can just pick up any here any square. So for example you pick up the square corresponding to coordinate 0 0. Now what is the arrow going out of it? So you say 2 left and 1 up. So the arrow going out is like this. And what is arrow coming into it? It also has to come from somewhere here, because then this is 2 left and 1 up. So this is how you make it. You just put in any arrow here, any module here. You want to say where is the arrow going out. So 2 left, 1 up. So this is what it is. And similarly, you know how the arrow is coming in. So you can make this. So for every square, in every square you can see that there is a module sitting, arrows is going out and arrow is coming in. So these arrows and these modules form a complex. So there is a complex on page 2, there's a complex on page 1, but notice that the arrows are going differently. Here the arrows are going in particular way, here the arrows are going in particular way. But again, this is the rule for putting the arrows. Now let us see page 3. So in page 3 you will have 3 left and 2 up. So page 3, so 3 left and 3 minus 1, 2 up. So again look at this module here. So you go 3 left, 1 2 3 left and 2 up, 1 and 2. Similarly, what is the arrow coming in here? It has to come from here, because from here if you go 3 left, 1 2 3 and then 2 up, 1 and 2, you reach here. Again, what is the arrow going out of here? You go 3 left, 1 2 3, 3 left and then 2 up, 1 and 2. So the arrow here goes like this. So again you can just put in any module here. So in every square sits a module. So what we are trying to do is trying to find out what is the arrow going out of it and what is the arrow coming into it. And this is the rule which is giving us. So again, what is arrow going out of it? You go 3 left, 1, 2, 3. 3 left and 2 up. 1 and 2. So we have to end up right here. So this is the how we are going to draw arrows. So on every page there is a chain complex. So what we do is, you're starting with page 1. So this is page 1. So corresponding to every module, you can compute its homology. So see, this is sitting here on this 2, 0. So this module is sitting at 2, 0, 2, 0. So you can compute homology here, and whatever homology you compute here on this square, you put the homology in the corresponding square on page 2. So on page 2, you take the same square, which is 2, 0, and you put the homology here. So you had a chain complex here, you compute its homology here, put it on the homology here on the second page. Same here. But now you have another chain complex here. So now again compute the homology here, and then you put this homology on the next page. Same place, 2, 0. So you have homology here. So when you're going through the book, you see what square lies under this square. So this is the square which lies under it. So homology of this is here. So, but this is another, if you compute homology, it's another module, and we have chain maps. Again, you can compute homology here, and you can go here. So more formally, you have an arrow going out from the square, and there is also an arrow coming into the square. So we are denoting on page R, this is the module sitting here. So this module is sitting at, say, 2 and 0. So on page 1 we have this module, and the corresponding coordinates are 2, 0. So you take the homology corresponding here, put it here. This is on page 2, so this denotes page 2, and you have 2, 0 is the coordinates of this square. So this is this square. So again, for this square, again the coordinates are 2, 0, but we are on page 3. So for this, so you have these sequence of modules sitting on every page, but you know that this page 2 is nothing but homology which you have computed in page 1, and page 3 is nothing but the homology which we have computed in page 2, corresponding to the arrows given to us. So this is how in general it looks like. If there is an arrow going from ER P plus RQ minus R plus 1 to PQ, or here basically this rule, R left and R minus 1 up. So you're going R left, so you subtract R from here, therefore you are P, and R minus 1 up, so you add R minus 1 to go up, you get PQ. And similarly here, to move R left you have to subtract R, and to move R minus 1 up you have to add R minus 1. So this is nothing but the arrows given to us. So here the arrow is coming from, this is again we are working in page 1, so this is coming from 3, 0. So you see that from 3 you're going to 2 because you have to subtract 1, you're going left. And you can just put this thing in at every coordinate and check. So this is our fundamental diagram. So this is given to you, and corresponding to this you can take homology, and this homology you put in the corresponding square of the next page. So you compute homology here for your chain complex, you know homology, kernel of the arrow going out over image of the arrow coming in. So kernel of the arrow going out over image of the arrow coming in, put it on the next page here, and so on. So the idea is, what you do is you take only the first quadrant. So that is for P less than 0 and Q less than 0, you put everything as 0. And therefore the only non-zero terms, they reside in the first quadrant. So this is 0, 0. So we have a lot of modules everywhere. So below this axis you put everything as 0. So all these modules living here are just 0 modules. And again all these are 0 modules. So other than the first quadrant, everywhere else you have 0 modules. So only non-zero modules live in this first quadrant. So again, only non-zero these modules live in this portion, the first quadrant. Everywhere else you have 0. So as you see, as you are moving through the pages, these arrows are getting longer and longer. So the arrows get longer and longer. So if you have particular fixed P and Q. So say you have fixed 2 0, ultimately these arrows will be so long that they will start from 0 and land in 0. So the arrows will start from 0 and land in 0, and this you can see easily, you know, if the r, so you have fixed these coordinates P and Q. So ultimately if the arrows start from 0 and land in 0, your homology is constant, because you know, if you have some homology group here, it goes here, you have like this, you compute its homology. Homology is just the kernel because image is 0, and kernel is this entire element here H, and therefore it just stabilizes. Now this will obviously happen if r is greater than maximum of this P comma Q plus 1. That is precisely because of this equation here. So say if this r is greater than Q plus 1, so if this r is greater than Q plus 1, then this is negative. Now if this is negative, that means that this is coming from 0 module and it will land in 0 module. So it's coming from 0 and landing in 0. So if this condition holds, this the arrow landing in the square PQ comes from the 4th quadrant, and arrow going out lands in the 2nd quadrant, because then P minus R is negative and this term is negative. So the arrow coming in comes from the 0 module, and going out also lands in the 0 module. So this stabilizes, and you can see this clearly, you know. So say you start with this coordinate 2 0. So here already you see that this E2 2 0, this arrow going in comes from the 0 coordinate, because this corresponds to -1 here, and everything non-zero lives above here. But notice that this is still not stabilized, because the arrow going out is not landing in 0. It is still non-zero. But on page 3 things are even easier, because on page 3 again you have the non-zero terms just live in this part. And now you can see this is already stabilized. This point is already stabilized because the arrow coming in is coming from 0 and it is landing in 0. So this is homology has stabilized. So after page 2, whatever homology you compute here, because this homology will depend upon the kernel here, so which may or may not be non-zero. So you compute the homology here, put it here, but once you put it here, after page 3 it is just going to remain the same, because if you compute the homology with respect to this module right here, it will just be the same again and again because of this. So you have eventually stabilized, and that's our hope, that as the arrows get longer and longer, the homology stabilizes. And you can go to infinite number of pages. You can go all the way to E infinite, but we don't have to worry about it. In most spectral sequences, the stability is achieved by page 2. So by page 2 things are stable. So by page 2 the things are stable, and then you can say something about the homology.